Yeah, so I'm going to talk about Arrow's theorem and various infinitary counterexamples to this. This is kind of outgrowth of a joint project I have with Walter Dean, who's my colleague at Warwick. So, okay, you can't see the top bit, but it's not super important. We're going to start off with a kind of classic paradox of social choice. Goes back to the 18th century, the Condorcet paradox. So suppose we have some kind of electoral scenario, people are voting in an election, or they're maybe trying to rank candidates for some kind of panel. So it's kind of plausible rule that we might have, majority rule. The majority of the electorate prefer some alternative X to Y. Then the social preference, the overall aggregated preference, should also prefer X to Y. Right? That's how we tend to elect people, at least if there's some kind of two-party election. So it seems like this is reasonable, but unfortunately it's not reasonable because it leads to inconsistencies with at least what we think one of these rules should be doing. So suppose we have a situation where we have three voters, A, B, and C, and voter A prefers X to Y and Y to Z. All of these examples will only work if you have at least three alternatives of candidates. You've got two, everything's fine. So in America, it's okay. No votes in Paris. Yes. Okay, so voter B prefers Y to Z and Z to X, and voter C prefers Z to X and X to Y. And of course, you can see immediately how this goes. A majority prefer X to Y, so A and C, and a majority prefer Y to Z, A and B, and a majority prefer Z to X, B and C. So what of these, what should be the overall aggregated ordering? X is preferred to Y, Y is preferred to Z. So by transitivity, presumably, if we're really capturing the notion of an order of preferences, then X should be preferable to Z. But of course, Z is preferred to X by a majority, so contradiction. And I suppose we call this a paradox, the Condorcet paradox. So when confronted with these things, you might think, okay, majority rule works in some situations, but not in all. And if we want a general theory about social decision-making, we should find some kind of rule, perhaps a class of rules that do work. So let's put down some conditions. Let's approach this axiomatically. And that's basically what Kenneth Arrow did in the end of the 40s, 1950s. So one thing we might say to try and diagnose this paradox is that, well, the preferences of the individual voters are transitive, right? So the individual voters are not doing anything wrong. They are expressing their preferences in a rational way. There are no cycles in their preferences. It's just in this aggregation rule that we're going wrong. So really, what we need to be focusing on is those ways of aggregating. And so we should have social preferences that are transitive, and presumably we want it that any two alternatives are comparable. So if we're faced with a choice of enacting policy A or policy B, we should be able to actually compare them. Have a social ordering that actually says, well, A is preferable to B, or B is preferable to A, or perhaps even that we're indifferent between A and B, but nonetheless they are comparable. And presumably we should allow that kind of indifference between alternatives. You can rule it out. You can just have linear preference orderings. It makes the mathematics a bit less interesting. In fact, you get the same reverse mathematics, but I won't go too much into detail on that. Okay, so this determines a kind of order notion called a weak order by social choice theorists, a total pre-order. Yeah, I should also say, if you just stick with linear orders, some of the results are easier, they're less fussy, but you get a few phenomena which are less interesting. It's kind of everything's a bit more boring. You can just stick with linear orders. So I just prefer this option. Okay, so here's the general setup that we have here. So we've got a set of alternatives. Yeah.
Can you go back to the slide?
This one.
So yeah, point 3 says that dies should be permitted, but that's a difference. But point 2 says that any two alternatives should be comparable. And is it possible? I mean,
yeah, it's a pre-order, so you know you can have.
Doesn't indifference mean comparability between two alternatives?
Well, you know, we have an ordering where it's like, you know, A, B. Strict. Here we have some kind of equivalence. This is strict. Yeah.
Okay, so B and C are comparable.
Yeah, these are comparable, right? We have this equivalence relation.
Okay. So we have to make a portion.
Yeah.
Okay,
Yeah, and this will be an equivalence relation. Okay, so we've got a finite set of alternatives. I'm always going to deal with finite sets of alternatives. You can have more if you want, but it messes up various things. So I'm going to stick with that. So if you've got a relation on X, a binary relation, which is transitive and strongly connected, then we call it a weak order. Okay. So just a few bits of notation. So precisely because we have this indifference relationship, we're going to have our orders be written like this. So X is at least as preferred as Y. So someone might be indifferent between the two, or they might strictly prefer X to Y, and we therefore have also X less than Y, X equivalent to Y. This means exactly what you imagine. Okay. And then we use W to refer to the set of all weak orders, and these are just counted by, I think they're ordered Fubini numbers. So if you've got 3 alternatives, there are 13, and then go up from there. So it's all exponentially determinable. Okay, so if you're working in Arrow's framework, as he originally developed it, more or less, we can think of a society as having the following components. So you've got a set of voters, the electorate. We've got a finite set of alternatives, X, and we can think of these as being candidates in elections or social policies that might be enacted, or perhaps even scientific theories we're deciding between. It's been applied to many different scenarios. And then we have this set W of all weak orders on X. And then we have a set of coalitions of voters. So we can think of people as maybe falling into all kinds of different groups. And in the original setup, in some sense, this notion of coalition doesn't play so much of a role, at least in the statement of the theorems, although it's important in the proofs. But the important thing for now is just that we think of this as being an algebra of sets. So it contains the empty set, it contains the set B of all voters, and it's closed under intersections, unions, and complements. And then we have a set of profiles. So I always found this word profile slightly confusing, but basically it just means like a voting scenario. So there might be a scenario in which I prefer X to Y, and some other scenario where I prefer Y to X. And Arrow's idea was to just consider all possible voting scenarios. It's this notion of unrestricted domain. So in the original setting, you can think about algebra A as just being the power set of V, and the set of profiles F as just being a set of all functions from voters into weak orders. Okay, so this is called the unrestricted domain condition. And since this is a reverse map talk, we're going to be having infinite V, and therefore you can kind of see where this is going. We're going to have to drop this condition, or at least weaken it substantially, in order to be able to actually talk about these things in second order arithmetic. Okay, so let's have a little bit of notation. I hope this is okay to read. We have like too many subscripts in this paper. I'm trying to cut down, so I'll say some more on that later. But basically, given a coalition, so some set of voters, we say that X is at least as preferred as Y by the coalition C under the profile F, if and only if, and just have the definition. Okay. So we're just thinking of this relation as being induced by this set given by the function. Okay. And then if we have two profiles and two alternatives, or perhaps more generally just some set Y of alternatives, then if the two profiles agree when they're restricted to those profiles, we just say that F is equal to G on that set of alternatives, or perhaps equal for some particular motor. So in this particular case, let's take X and Y, you say, okay, whatever F and G are, they agree with respect to F and Y's, at least as far as B is concerned. So the two profiles, you know, X is at least as preferred as Y for B. And this doesn't say anything about the other alternatives. So you might have that we've got X less than Z less than Y, or X less than Y less than Z, or whatever. The important thing is just the relative position of X and Y. Okay. And this is important for formulating one of Arrow's conditions. Okay, so this is just what I'm saying. Okay, so those are societies, and then given a society, you might imagine many different agrodecimals or social welfare functions, as they're called. So the idea of a social welfare function is just you plug in a profile, so an election or a scenario of some kind, and it will produce a weak ordering of the alternatives that corresponds to you know, what the society wants to happen overall. Okay, and then Arrow imposed various conditions on these social welfare functions, one of which is pretty plausible, I think, unanimity. So if every voter prefers alternative X to alternative Y under scenario F, then so should the society as a whole. So that at least seems fairly uncontroversial. The second is called independence of irrelevant alternatives, which is kind of a mouthful, so I'm just going to call it independence. Basically, the idea is simply that if you have two different voting scenarios, two different profiles, then if they agree with respect to the order on, if all of the voters in those two profiles agree with respect to the ordering of two alternatives, X and Y, then the social welfare function should also agree in both cases. So it shouldn't care about relative position, say, in this set, right? As long as all the voters agree, well, X is less than Y, it doesn't matter where Z comes up. So, stating it more formally, for all subsets Y of X and all profiles F and G, if F is equal to G on Y, then the social welfare function, sigma, should give you a weak ordering in both cases that agrees on Y. And in the typical case, you know, Y is just going to be two alternatives, but we state it a bit more down. Okay, and then finally, non-dictatoriality. So the idea is just that no single voter should be able to impose their will on the whole society. So there shouldn't be any voter who always gets their way. Obviously, this in the social choice theory and economics and political philosophy literature, it's laden with a certain, I don't know, moral valence, but we can just treat it as a mathematical condition. But for all profiles, for all voters, there exists a profile where they prefer x to y, but the social welfare function prefers y to x, or at least ranks x at least as highly as y. Okay. All right, but then, these conditions all seem fairly reasonable, I think, more or less plausible, certainly the first and last, but unfortunately they don't really work. So suppose we've got a society which satisfies the universal domain condition, and B is finite, and the number of alternatives is at least 3. Then there's no such social welfare function, right? There's none that satisfies unanimity and independence and non-dictatoriality. So you can get 2 out of 3, but you can't have all of them. So this is Arrow's theorem. It's kind of foundational theorem, really. In social choice theory, you might say the foundational theorem. It's inspired a huge amount of work, debate, and controversy. So here's a kind of controversial quote from a political scientist called Recored. So the main thrust of Arrow's theorem and all the associated literature is there's an unresolvable tension between logicality and fairness. Independent choice requires concentration of power in sharp conflict with democratic ideals. So this is, kind of fiery, but we don't need to worry too much about this. It's fair to say that this is something that people take quite seriously. I'm not sure if we should, but they do. Okay, so fast forward like 20 years. Sorry?
Your brief time.
The title.
Oh, okay. So, I mean, it's meaningful, I think. We'll see. So, all right, fast forward 20 years from 1950 to 1970, and this mathematician called Peter Fishburne produced this very nice, very short paper and showed that, well, if you allow B to be infinite, then you can get out of Arrow's theorem. It's only the finiteness that's holding us back. And the way he did it was to use an non-principal ultraviolet on. Very good. To use a non-principal ultrafilter on B, and this lets you produce a social welfare function which satisfies unanimity because B is in the ultrafilter, of course, and satisfies independence and satisfies non-dictatoriality. There are no finite sets, so there can't be any dictator. The dictator is the element that generates the ultrafilter. So suppose you've got a society that satisfies universal domain and is infinite, then there's a social welfare function which satisfies all 3 of Arrow's conditions. Okay, and the proof is fairly straightforward. But of course, Fishburne's result uses some choice. I mean, not all of choice, but some choice. And the guys have this non-principal ultrafilter. And this sort of sparked a bit of debate amongst social choice theorists that, I mean, it's still kind of going on today since the paper from 2018, about non-constructive methods in social choice theory. And, are these results really meaningful? So in some sense, we can see, the results I'm going to present today as kind of addressing this issue. Okay, so in the proof of Arrow's theorem, Arrow uses this notion of a decisive coalition. So a coalition that, like a dictator, always gets its way in every profile. If they prefer x to y, then x is going to be preferred to y by a social welfare function. So suppose we have a society, then we say that a coalition C is sigma decisive if for all profiles F and all alternatives x and y, if x is strictly preferred to y by everyone in C, then x can be preferred to y by the social welfare function for profile F. Okay. And this lets us rephrase dictatoriality. So a voter D is dictatorial just in case the singleton of that voter is sigma decisive. Okay. So we're just going to be using this sort of reformulation of dictatoriality and this understanding it through the lens of this more general notion of sigma decisiveness. And this notion of decisive coalition is the basis of this very nice paper by Kerman and Sonderman from 1972. So I'm building on Fishburne's results. They kind of prove the other direction. So Fishburne shows, oh, we've got a non-principal ultrafilter, then you can go to a non-dictatorial social welfare function. They said, oh, you can go the other way. You can just start with a social welfare function and you extract an ultrafilter of decisive coalitions. So the set of decisive coalitions forms an ultrafilter. That's their main theorem. So suppose that you have a society S satisfying universal domain. I mean, they don't explicitly say satisfying a universal domain, it's just there in the background. And you've got 3 or more alternatives, and you have a social welfare function that satisfies unanimity and independence. So we don't require that it satisfies dictatoriality. In order to get the ultrafilter, you only need unanimity and independence. And then the kind of ultrafilter you get will depend on whether or not the social welfare function is dictatorial. So if you have those conditions, then there exists this ultrafilter U sigma on your algebra of coalitions, in their case, just the power set algebra, which is just the set of sigma decisive sets. And the ultrafilter is principal if and only if the social welfare function is dictatorial. And of course, in the finite case, all ultrafilters are principal, so it's always going to be dictatorial. But note that this is provable in ZF, right? And that is enough to show that Fishburne's possibility theorem isn't provable in ZF, right? Because it implies the existence of a non-principal ultrafilter. So assume Fishburne's theorem in ZF, apply this theorem, and you get a non-principal ultrafilter on any infinite set V you like. Okay. For some reason, this is not. People know about this, but nobody ever actually comes out and says this in the literature for reasons that are slightly beyond it. Anyway. Okay, so now we've got some theorems. So now we can do some reversal backwards. Okay, so there are some fundamental challenges, obviously, for formalizing this stuff in second-order arithmetic. One is cardinality, obviously. So if you have an infinite set of voters, then the unrestricted domain condition is not going to work, because you're going to get continuum many profiles, continuum many coalitions. And obviously, in such a case, the social welfare function and the ultrafilter are also going to be uncountable objects. So in particular, this is problematic because we can't quantify over them, and it makes stating everything kind of a pain. The other issue is, of course, effectiveness. So definitions need to be tractable in the base theory. So the framework I'm going to introduce now is really basically set up to handle these two problems as I encountered them in trying to formalize this stuff. Obviously, there are a bunch of different approaches that have been taken to the use of ultrafilters in reverse mathematics. So one might be just, let's use a higher order framework like Colombach's, RCO 0 omega, and then, then we can talk about it directly, but this system is kind of a pain to work with. I'd rather work with just second order arithmetic. Second is to follow Henry Townsend's paper from 2014. We just extend the language with an additional parameter, or in this case, 2 additional parameters, one for the social welfare function and one for the associated ultrafilter. And you can do this. This is actually what I started out doing. But then, I also found this was a little bit unwieldy, and it was sort of nicer to get results just based on the third approach, which is just restricting our attention to countable societies. So obviously, V itself is going to be countable. It's just a set of natural numbers, but the algebra of coalitions and the set of profiles are also going to be countable. So we're going to be dropping arrows, unrestricted domain condition. Okay, so set of voters will be a finite or infinite set of natural numbers. Alternatives will just be some finite set. I guess I'm sticking to just calling it a finite set of natural numbers, but you can obviously just think of it as being a natural number, if you like. And for coding purposes, of course, that's exactly what it is. And then to address the cardinality condition, we just think of, instead of having profiles as being sets themselves. They are all coded into a sequence. So we have a countable sequence of profiles. So a countable sequence of functions mapping voters to weak orders. And then we're going to have to impose some conditions on these sequences. So just a point on notation. I'm not sure if you can see, but here we just have I, the index of the function in the sequence, rather than F, which is not really very meaningful. So now we just care about the index of the function. And then we're going to restrict the set of coalitions to countable algebras, and in fact, countable atomic algebras. We always want all of the singletons in there, because otherwise we're not going to get any dictators. So at least we want the possibility of having dictators in there. And this approach, of course, means that we also get all finite sets and all co-finite sets. So in some sense, the minimal algebra you get is the finite co-finite algebra, at least as long as V is infinite. And again, like V, if it's infinite, you could just think of it as being the natural numbers. None of the results change if you do. In general, I just will let it be any infinite set, but it's not particularly important. Okay, so then this is just the standard definition. Atomic countable algebra of sets over V is a sequence of subsets of V, which contains V and all of the singletons, and is closed under intersection and complement and union. This kind of move was already made in the literature, in fact, all the way back in 1980 by this guy Armstrong, and he generalized the results of Gell and Sondermann to these algebras, and he had a particular way of getting a set of profiles from each algebra. I have to say that if you go and read his papers, I'm not sure that all of his results quite work, because he really needs some auxiliary conditions that he doesn't actually give to make all of the results go through. So I would say be a bit careful with this literature. Yeah, and sometimes, of course, we're going to need to compute the unions and so on in a uniform way. And so we're just going to assume that we're working with some algebra that we've reordered in a computable way to ensure this. Okay, so having moved to a countable algebra of coalitions, we then need to make sure that we have enough stuff in the set of profiles. It can't just be any random set of profiles. It needs to be somehow associated with this algebra of coalitions, basically just to make the proofs go through. There are various conditions that have been looked at in the literature, but I think that very often people in social choice theory are not thinking about the infinite case, and the conditions that they impose actually always end up, they might not give you universal domain, but in a case like this where you've got a countable set of voters, they're always going to give you an uncountable set of profiles. So they're actually much stronger than are really needed. So Armstrong, for example, just says, okay, let's take F to be all of the A measurable profiles. So just the profiles such that for every pair of alternative sets of Y, the set of voters who prefer X to Y under F is in the algebra. Okay, so it's the profile is measured by this algebra. If you arithmetize this definition, though, you get something that's sigma 2, and it's not really very good to work with in RCA0. So instead, we're going to require that for every I, the profile Fi is measurable, but measurable by a sort of uniformizing function that's built into this definition of a society. You can prove that these uniformizing functions always exist in ACA0. So this is an RCA0 version of measurability. yeah, so I'm just going to call it uniform A measurability. So suppose that we have V and X as before, and a countable algebra of sets A, and then we have a countable sequence of profiles, and then we say that F is uniformly A measurable by this function theta, just in case theta takes as an index for a profile and a pair of alternatives, and gives you back the index of a set in the algebra. Okay. So it does the measuring for you. So that's one side of this problem of richness, but the other is that actually you need to impose some further conditions. Somehow, that gets you that enough stuff is going to be in A, but you also need that there's enough stuff in F that reflects the structure of A, and not just the structure of like individual sets and their complements, but actually like finite partitions, basically, of A. In fact, when I say finite, that's really an exaggeration. You don't need any finite partition. In fact, all you need is about 4 or 5, at least for the proofs I'm going to be talking about today. Although I recently found that sometimes you need a little bit more than that, but typically you don't need that many. So one issue is that, okay, you can just say, well, we have to require that F always contains profiles that basically code up finite partitions. Yeah? We take our set of vectors V, and anytime you've got some finite partition, then we're going to just color each of these subsets with a different weak order. R1, R2, R3, R4. Of course, we only have a certain number of these weak orders, and that bounds how many, the size of these partitions, but that's not a problem for these proofs, which is good. But checking that you've actually got some finite sequence of indexes which forms a partition, that's not computable. For one direction of these proofs, that's not a problem, but if you want to start building these Fs from the algebras, then you need to do it in a computable way. And so if you have something non-computable coming in, that's a problem. So instead, we do something called quasi-partitioning. So the idea is roughly just, okay, take a sequence of indexes from A, and the sets at those indexes might overlap. And if you do, just take anything that overlaps and just chuck it into the big bin at the end. So we've got V, you might have some set that covers this bit, and there's some set that covers this, right? And there's some stuff, maybe even some stuff left over. There's some stuff that's in two things. So then we just take this part where there's no overlap, and we send this to one ordering. We take stuff in here where there's no overlap, send it to another. Stuff in here where there's order races. And then these parts where there's overlap, we're just going to map them all into some final thing. Okay, and this gives us something that's always well defined. And then when you're actually doing the proofs, you can just construct the partition, right? Sometimes you're just able to partition things, and then you will get an actual, coloring that really partitions the. Okay, and then again, we want some kind of uniformity, so we want some way of computing these quasi-partitions. So we say that A is quasi-partition embedded into F if there's some map E, which takes a sequence of indexes in A and some permutation of W, right? Because we want all of the possible orderings. And it just sends the elements that appear, say, only in one of these sets. So we've got V and it only occurs in here, not in anything else, it gets sent to some unique order, and so on. Okay. So this is kind of technical, I think, with respect to the usual conditions that you see in social choice theory, but it works quite well. I sort of, this is kind of an empirical sort of feeling to it. Like, I worked with proofs for a long time, and this is what I extracted to make everything go. And I thought maybe this is a bit ad hoc. Maybe this doesn't work for other proofs in social choice theory, but in fact, recently I was working on some results about strategic voting theorems, and I thought, okay, maybe this condition isn't strong enough. I need some more stuff, and then I realized actually it gives you exactly what you need. So maybe it's a bit more natural than I thought. Yeah, this is just the formal definition, which is kind of horrible, so I won't spend any time on this. Okay, so we combine these definitions and we get the notion of a countable society. Okay, so a countable society is a non-empty set of voters, a finite set of alternatives greater than or equal to 3, an atomic countable algebra on V, and a countable sequence of profiles such that that countable sequence of profiles is uniformly A-measurable, and the countable algebra, the coalition algebra, is quasi-partition embedded into F, okay, which is kind of a mouthful. In some sense, all of the work is in this definition, and then everything else is relatively straightforward, I would say. Okay, and then a countable society is finite, is finite, and infinite otherwise. Okay. And then a social welfare function is just one that satisfies, it's a function from indexes of profiles to weak orders, and it satisfies unanimity and independence. And if it satisfies the obvious formulation of non-dictatoriality, then it's non-dictatorial. So the definition of a social welfare function is just the same as arrows, more or less. Okay, so then we can finally state this Sondermann theorem for countable societies. So it just says for all countable societies and all social welfare functions, sigma for a given society, there exists a set U, U sigma, consisting of the indexes of the sigma decisive sets, and it exists, it forms an ultrafilter, and its principal, if and only if sigma is dictatorial. So it's really just reformulating their statement in terms of this notion of a countable society. Arrow's theorem just says if you have a finite society and a social welfare function for that society, then it's dictatorial. And Fishburne's possibility theorem for countable societies just says, well, if you have a countable society and it's infinite, so set of voters is infinite, then there exists a non-dictatorial social welfare function for that society. Okay. So all of the statements of the theorems just come out immediately from this definition of countable society. Okay, so the first thing you want to do if you have a setup like this is say, okay, I've formalized Arrow's theorem, I've formalized all of this machinery. I should probably prove Arrow's theorem, right? So let's prove Arrow's theorem. Okay, so one additional notion that I will mention that is not strictly necessary to go through in detail is the notion of almost sigma decisiveness. So because we have weak orders, we have potentially indifference, right? So if you have two alternatives, X and Y, you can always think of the set of voters for a given profile as being partitioned into 3. Those who strictly prefer X to Y, those who strictly prefer Y to X, and those who are indifferent between the two alternatives. Okay. So an almost sigma decisive set is one where, when it's the case that everyone in that set prefers strictly X to Y, and everyone not in that set strictly prefers Y to X, then the social welfare function always agrees with everyone in that set. Then we say that set is almost sigma decisive. So that's the second definition. The first one is just like at a given profile. And we then have this nice definability lemma for sigma decisiveness. In some sense, this is really the heart of things. Quite a lot of this is already in, for example, Kerman and Sonderman's paper. Some of it's implicit in what arrow does, but it's nice to sort of put it all together. So this is provable in RCA0. Suppose you have a countable society, it could be finite, it could be infinite, doesn't matter. Then there's a function from natural numbers to natural numbers and a pair of alternatives x and y, such that the following are equivalent. AN is sigma decisive. I mean, yeah. So in some sense, we're moving from stronger to weaker conditions. So AN is almost sigma decisive. And there exists some index K and some pair of alternatives X, Y. I should probably have used different things. Let's call them like, W and Z or something, right? Such that AN is almost sigma decisive for K at W and Z. So this is kind of important because at the top we have this global condition, right, that applies to all profiles, and this one just applies to one, right? So it's saying if you've got this, if you've got some coalition that wins somewhere, they win everywhere. And this is where you need three alternatives, basically, to do this transfer of, or this spread of decisiveness from one particular profile to all of them. So in some sense, this is where the matching happens in Arrow's theorem. But in our setting, we can get something more. So one thing to notice here is that the first condition is pi 0,2, and the third is sigma 0,2. So what this shows is that if you've got this social welfare function, sigma, then the set of sigma decisive indexes for sigma decisive sets is delta 2 relative to that social welfare function. So it's computable in the jump of the social welfare function. But actually, the last condition lets us do something even better, because we have this function g, which we can prove exists in RCA0. It's a computable function, and some particular pair of alternatives, such that just comparing those two alternatives will allow you to determine whether or not a particular index is an index of a sigma decisive set, right? So it's computable. And this is what allows us to prove the Kerman-Sonderman theorem in RCA0. So by the definability lemma, the set U sigma of indexes for sigma decisive sets exists in RCA0, and then we just formalize the Kerman-Sonderman proof, basically. So the proof that I have is really just very similar to theirs. And you go, look, this forms an ultrafilter on A, and its principal, if and only if sigma is dictatorial. Okay, so this Kerman-Sonderman theorem for countable societies is provable in RCA0. And then this just gives you Arrow's theorem, because ultrafilters on a finite set are principal, and you can prove this in RCA0 too. So we have that Arrow's theorem is provable in RCA0. Okay, so in some sense, success, right? And we can do a bit better as well. Arrow's theorem is about finite societies, so we can just code up all of these finite societies by natural numbers, and thereby obtain a pi01 formalization of Arrow's theorem. Here, you do have to do a couple of additional things, putting in some extra bounds in some of the proofs if you want to do it properly. But you get this pi01 formalization of Arrow's theorem, and it follows from the second order formalization, again, once you put in this extra bounds. And then by pi02 conservativity, we get that this first order formalization of Arrow's theorem is provable in PRA. In some sense, this is obvious if you look at proofs of Arrow's theorem, but as far as I know, no one actually pointed this out before. In fact, I think you can probably do better. I think you can probably prove it in I delta naught plus x. I'm not going to, but if someone would like to, I'm sure it would be a nice project. I'm not sure how much of the proof of the Kalman-Sondermann theorem as it stands goes through in something like RCA 0 star. I think it might be annoying because there are various points where it uses sigma 1 induction, but probably something that works in I delta naught plus x can be extracted if you're just working with finite societies and you know that there are these fixed bounds of things. Okay, so that was two about theorems, Arrow's theorem and the Kalman-Sondermann theorem. So what about Fishburne's possibility theorem? I'll first quickly mention sort of extension of this idea of non-dictatoriality. So we know that we can only have this in the infinite case, but we can generalize this idea, right? So you start out non-dictatoriality about the existence of one dictator. What about more dictators? If you've got a coalition of size k, is that enough to get you, does that get you something different? So let's say that sigma is k non-dictatorial if there's no, if you, I'm not sure I can phrase this very well, but basically if you have any sequence, therefore coding a finite set that is less than or equal to k in length, then there's some j and some pair of alternatives x and y such that everyone in the finite set coded by this sequence prefers x to y. The social welfare function ranks y at least as highly. So it's just non-dictatoriality, but for some set of cardinality k. And then the uniform version, sigma is finitely non-dictatorial if it's k non-dictatorial for k. And finally, say sigma has the cofinite coalitions property. If whenever you have cofinite many voters preferring x to y, then the social welfare function also has to prefer x to y. And it's obvious that any social welfare function constructed in the way that Fishburne does it will satisfy this, right? Because it's coming from this ultra filter. So it's really just a question like, do we get anything different? And in some sense, unfortunately, the answer is no. So yeah, consider FPT K and FPT less than N and FPT plus to be FPT, but replacing non-dictatoriality with these three traditions. And then following equivalent over RCA 0, FPT, FPTK for any fixed K, and FPT less than M, and FPT plus. So these are all equivalent. Proving this is just, you do a sigma 1 induction showing that basically if you have all you need to prove really is that 1 implies 4. So you just show, okay, if I've got a coalition of size k, then its complement is sigma decisive, and you just do induction. But these are also all equivalent to ACA 0, as you might expect. So we've got the equivalence of 1, 2, 3, and 4. So all we need to do is show that FPT implies ACA 0, and that FPT can be proved in ACA 0. So to do that, we just use the following well-known results that over RCA 0, ACA 0 is equivalent to the statement that whenever you have a countable atomic algebra over an infinite set, there's a non-principal ultra filter on that algebra. It's just like a minor variation, but well-known equivalence. So let's work in RCA 0 plus FPT, and we fix some countably infinite atomic algebra A. And the idea is we're just going to show there's an ultra filter on this, whatever it is. So to do that, we need the following lemma, provable in RCA 0. So suppose, as usual, we've got a non-empty B and a a finite set of alternatives X and a countable algebra over V. And notice here that we don't assume that V is infinite, because the lemma applies quite generally. Then from the algebra, you can construct a set of a sequence of profiles F, which give you a society. So they are uniformly A measurable, and A is quasi-partition embedded into F. Right? So you can just do all of this computably. You take your algebra and you computably build at the same time the sequence of profiles and the two embeddings. And it's basically just a really tedious exercise in primitive recursion. Okay, and then just say, okay, let's take V to be the natural numbers and take X to be 3. And by the lemma, we've got this countably infinite society based on our original algebra A. By FPT, we've got a non-dictatorial social welfare function. And then by KS, there's an ultra filter. And because the social welfare function was non-dictatorial, the ultra filter is, sorry, the repetition of non-dictatorial, non-principal. So that suffices to give you ACA 0. Okay, so that's the reversal. For the forward direction, you really just take Fishburne's proof. Okay, so just take, so we break it up firstly into this lemma where I guess all of the work happens. So suppose you've got a countable society and an ultra filter. So the society could be finite, the ultra filter could be principal, doesn't matter. And then from that ultra filter, you can define a social welfare function such that the ultra filter consists, it gives you the decisive coalitions. So you get a social welfare function, sigma u, which is dictatorial if and only if u is principal. So when we went the other way, when we proved the Kahneman-Sunderman theorem, we started out with the social welfare function. We got this ultra filter of decisive coalitions. So the ultra filter was unique. This way is not unique because of these weak orderings. So there might be things where the ultra filter doesn't determine exactly what the social welfare function is going to do. So you're going to have a bunch of different ones. So it's a partial converse to the Kahneman-Sunderman theorem. Okay, so now working in ACA 0, take account of the infinite society. And then by the lemma, there's a by the lemma from the previous slide, there's a non-principal ultra filter on A, doesn't matter which one. And by this partial converse to the Kahneman-Sunderman theorem, there's a non-dictatorial social welfare function. And that's Fishman's theorem. Okay, so as I said, the proofs are easy. The lemmas are either kind of lots of primitive recursion, or they are formalizations of the original proofs in Fishburne or in Kahneman-Sunderman. So everything transfers very smoothly once you have the right definitions. I've been here over the last few days looking to think, is there more that we can do? So I just have a few kind of questions that maybe are obvious to people. So one thing is just like, can we have a more revealing computability theoretic analysis of these non-dictatorial social welfare functions? Can we find out something more interesting than just a reversal to ACA 0? So by the Kahneman-Sunderman theorem, we've got the ultra filter U sigma induced by sigma is computable relative to it, but it's not generally an equivalence. You can have, for example, you can have dictatorial social welfare functions which are not computable. But of course, if the ultra filter is principal, then it's always going to be computable, right? Because it's generated by a single element. So you just take an index, check whether that element is in there, if it is. Right? So that's the procedure. But sometimes, basically, because of this fact that we have these weak orders, you can have a dictatorial social welfare function which is not computable, just by deferring the bits that are undecided by your principal ultrafilter to some non-principal ultrafilter. Yeah, so I call this a sort of filling in construction. So yeah, it would be nice to know if we can also have this for non-dictatorial social welfare functions and exactly how it works. Yeah, so then also like for the construction of the ultrafilter, at least the construction that I know, this gives us a non-dictatorial social welfare function, sigma, with EA degree relative to the double jump of the society. So can we bring this down a bit? Do ultrafilters have to be this complicated, or can you do better than this? And then conversely, all the reversal does is at least, applying the usual way that this is proved, is show that if you've got a non-dictatorial social welfare function, then you get the jump of the society, right? It's just the usual curvy construction. So can this be strengthened? Can you get something more interesting out of it? Okay. So I seem to be running out of time, which is what I thought would happen. But if people like, you can hang on for another 5 minutes. I can quickly go through something that I'm working on at the moment that's sort of related to this. No, nobody's giving me like flaring daggers at me. Okay, I'll go over it. So, okay, this is about different set of results also in social choice theory, kind of applying this framework. So let's call a social choice function, a function from our set of profiles to our set of alternatives that selects a single winner for elections. So voters are still going to be giving ballots that are rankings basically, but the social choice function is going to say, well, we've aggregated all the ballots, and in this election, this person is the winner. So in the 70s, Ibbard and Satterthwaite investigated the idea of strategic voting or tactical voting. People call it different things. The idea is that you might misrepresent your preferences in order to get the result that you prefer. And they prove the following theorem. So if you've got a finite society and a social choice function which is immune to strategic voting, then that social choice function has to be dictatorial. It's always going to be determined by a single voter. So this is in a way very similar to Arrow's theorem, and in fact, I think you can use Arrow's theorem to prove this. Okay, so suppose you've got a society S and a social choice function. We say that C is manipulable at some profile N by a voter B if there's some K, some profile K, which is different at B. So B has different preferences for the two profiles. So they have their, what they want and what they're going to pretend that they want in order to get what they want. And then for every other voter, they have the same preferences in these two profiles. And the social choice at K is better for voter B than the social choice at profile N. So they've gone from a less preferred alternative to a more greatly preferred alternative by changing their expressed preferences. So that's manipulability. And then we say if the social choice function is not manipulable at any profile, then it's strategy proof. And then, 77, Hasler and Wesley proved that if you have an infinite society, basically by the same kind of proof as Fishburne, then there's a non-dictatorial strategy proof social choice function for the society. So strategy proof social choice functions in the finite case can be given this kind of alpha filter analysis. Right? So it all works out just like in the kernel sampling theorem. really as you would expect. But this doesn't generalize nicely to the infinite case. So here's a better definition for the infinite case. Suppose we've got S and C as before, then we say C is coalitionally manipulable at a profile Fn by a coalition AM. If there's some profile, again, we have a group of voters and they're going from their true preferences to the ones that they're pretending to have by changing their votes. Everyone else votes the same, and at this other profile, they get something better. And then we say that C is coalitionally strategy proof if it's not coalitionally manipulable. And this does give you this ultra filter analysis in the infinite case. And again, you get this theorem. So in fact, you can just take the previous theorem as a corollary of this. If you've got an infinite society, then there's a non-dictatorial coalitionally strategy proof social choice function for the society. And then you can prove that these two things are equivalent. The existence of coalitionally strategy proof social choice functions for infinite societies and Wishburn's possibility theorem. So it's a kind of way of going from social choice functions to social welfare functions and going from social welfare functions to social choice functions. The former is harder because you don't get as much information in a social choice function. You have to work a bit harder to make it all go through. And of course, this gives you an equivalent to ACA theorem. So this theorem of Mehara, I think, is possibly of interest. So he showed that there's a countably infinite society and a non-dictatorial social choice function, which is individually strategy proof, but not coalitionally strategy proof. So it doesn't determine an ultra filter. So I think another nice open question is, what's the strength of this statement, or just the statement that for every countably infinite society, there's an individually strategy proof social choice function? Does that just give you ACA 0, or is it more interesting? So that's the last thing. Thank you.